Good afternoon, students. Today we will start with the chapter P block elements, and under this we are going to start with group 15 elements, which is also known as nitrogen family or pnictogens. So first we will have a look at the elements which are present in this group. We will see their electronic configuration. We will judge the general configuration for those elements. Then directly we are going to start with the chemical properties, and under chemical properties today we will be discussing about the oxidation states, right? So let us have a look at the elements. So it's nitrogen, then we have phosphorus, then arsenic, antimony, bismuth, right? Now if we consider nitrogen, its atomic number is 7. So what about the configuration? So it is having a configuration like this: helium 2s2 2p3. Next, for phosphorus it is argon 3s2 3p3. For arsenic it is krypton 3d10 4s2 4p3. For antimony it is xenon 4d10 5s2 5p3. And last one, it is radon 4f14 5d10 6s2 6p3, right? So if we have a look at these configurations, what about the general configuration if we want to consider? So the general configuration is ns2 np3, right? Since it's a p-block element, we can consider it generally as np3, but if we have a look at the last shell, so it is np2 ns2 np3, right, students? Now let us start with the concept of oxidation number here. Okay, so what is oxidation number? Oxidation number is nothing but the charge of an atom in a given species. Okay, so if it is in the normal elemental state, there is some value of oxidation state. If it is in the molecular form, there is some value of the oxidation number. If it is in the form of a compound, there is some value of oxidation number, and it also depends upon the electronegativity of the other species involved in that particular compound, right? Now if we have a look at nitrogen, it is the very first member of this group. So if we consider the first member of the group, they have some anomalous behavior. So what are the anomalous behavior for nitrogen? So anomalous nature or behavior of nitrogen, since it is the first member. Okay, so the first point is it has an exceptionally small size. Right? So we all know that the first member of a group will have a small size, but the size of the first element is much more smaller than expected. Okay, so we are writing here exceptionally small size. Next, point number 2. They have very high electronegativity as compared to the other elements of the group. And the third one is there is no presence of any vacant d orbitals. So unavailability of vacant d orbitals. So these are the 3 main anomalies of nitrogen as compared to the other elements of the group. Now let us proceed with the oxidation states. Now we all know that the oxidation state can either be 0, positive or negative. But generally, a negative oxidation state is fetched when an element goes for gaining of electrons. Similarly, an oxidation state of positive is obtained when an element goes for sharing of electrons. Now, since the configuration of nitrogen is 2s2 2p3 and there is no availability of any vacancy orbitals for nitrogen because there is no concept like 2d, okay, so nitrogen is very much electronegative also, and since it's a non-metal, it will go for gaining electrons, and as a result it will give rise to an oxidation state of -3. Okay, now let us have a look at phosphorus. So phosphorus has a configuration 3s2 3p3, right? So there is a vacant 3d orbital. So phosphorus being a non-metal, it has 3 unpaired electrons, it is 3p3, so it will gain 3 electrons due to its non-metallic nature, so it will give rise to an oxidation state of +3. In addition, it can share 3 electrons, so it can give rise to an oxidation state of +3, and it can also give rise to an oxidation state of +5. So how it's giving rise to an oxidation state of +5? Let us have a look here. So if phosphorus is 3s2 3p3, I'm not writing the full thing. So this is 3s subshell, this is 3p, and if the last electron is moving in the third shell, so it has a completely vacant 3d, right? So the configuration is actually this 3s2 3p3. So since 3 unpaired electrons are there, it can go for sharing of 3, so an oxidation state of +3. Additionally, this one of the electron from 3s can be excited to 3d. Okay, we can go for this kind of an excitation, and if this excitation happens, so what we are going to get is totally 5 unpaired electrons. So totally 5 unpaired electrons means it's going to generate an oxidation state of +5. So we have written here it also forms an oxidation state of +5. Now let us have a look at arsenic and antimony. They are not non-metals and they are not going to gain electrons as such. Okay, so they have 3 unpaired electrons in 4p and 5p respectively, and 4s and 5s electrons can also be excited to 4d and 5d. So they can generate an oxidation state of +3 and +5 both. Now let us concentrate on bismuth. Okay, so bismuth has a configuration which is 6s2 6p3, right? So it has 3 unpaired electrons, so it can generate an oxidation state of +3. But the 6s electrons which are paired, they cannot be excited to 6d. Why? Because 6s electrons are preceded by the 4f electrons. So due to the presence of these intervening 4f and 5d electrons, which very much incompletely shield the nucleus properly, as a result what happens, the effective nuclear charge highly increases. Okay, so if the effective nuclear charge will highly increase, so that's going to hold the outermost electrons very tightly. Okay, and as a result what's going to happen, this excitation becomes difficult. Now if the excitation becomes difficult, this is applicable for both 6s and 6p, right? Now what I have mentioned here, that 6s electrons cannot be excited properly. Why? Because in addition to this screening or shielding effect, another effect is also playing a vital role, that is penetration effect. We know that if we consider s, p, d and f orbitals, s orbitals have maximum penetration effect, then p, then d and then f, right? So due to ineffective shielding, both the 6s and 6p electrons are tightly held, but 6s electrons are much more tightly held due to their higher penetration power. So if we combine these two effects, 6s electrons cannot take part in any kind of excitation and hence in any kind of bond formation. So 6s electron behaves as inert pairs. This is, as we know, is known as inert pair effect. So bismuth shows an oxidation state of +3 only. Why? Because +5 state is not possible due to inert pair effect. Okay, so +3 only due to inert pair effect. Right? So that's all for today's class.